10A, Total Mechanical Energy. 10.1 Conservation Laws. Scientists acknowledge that no truly creative processes can be observed today because of the existence of conservation laws. A conservation law states that something is conserved. That is, something remains constant under certain conditions. For example, you learned in the last chapter that a system's total mechanical energy remains constant as long as no non-conservative work is done on the system. Scientists have discovered that mass and electric charge, as well as energy, seem to be conserved in all processes except under the most extreme conditions, when total mechanical energy is not conserved. 10.2 Air resistance. Under what conditions is total mechanical energy not conserved? When work is done on the system by non-conservative forces, the total mechanical energy changes. This work is often done by frictional forces. One kind of frictional force is air resistance. If you put your hand just outside the window of a moving car, you will feel air resistance. It is a reaction force. Your hand, moving with the car, pushes on air molecules, so the air molecules push back on your hand. If the car goes faster, you must exert more force to keep your hand in the airstream, as the force of air resistance increases on your hand. Consider a raindrop falling through the air. There are two forces on the drop: the force of gravity pulling it down, and air resistance pushing upward against it. As the drop's velocity increases, the air resistance on it also increases. Eventually, the drop's velocity is high enough that the air resistance balances the force of gravity. The drop stops accelerating and continues to fall with a constant velocity. This velocity is called the drop's terminal velocity. We are fortunate that air resistance prevents raindrops from accelerating throughout their fall. Otherwise, raindrop falling from 6,000 meters would be traveling at nearly the speed of sound by the time it reached the Earth's surface. When the raindrop reaches its terminal velocity, its kinetic energy remains constant. However, since it falls, its potential energy decreases. What happens to the potential energy that the drop loses? It is changed to thermal energy and lost as heat into the air and within the raindrop. When an object falls through the air, its temperature increases. In a short fall through the air, the rise in an object's temperature is not measurable. However, in a long or high-speed fall, this temperature increase is important. For example, when a spacecraft falls through the Earth's atmosphere, its temperature may exceed 2,500 degrees Celsius. Therefore, all spacecraft intended to return to the Earth must be protected by heat shields. The tragic loss of the Space Shuttle Columbia in 2003 is believed to be due to a breach in the integrity of its heat-shielding tile system. Thermal energy is not included in an object's total mechanical energy. If potential or kinetic energy is changed to thermal energy, total mechanical energy is not conserved. Thus, for an object's fall through the air, total mechanical energy is not conserved. Spacecraft engineers use atmospheric drag to significantly slow the vehicle from orbital speed before it reaches an altitude in the atmosphere where other means are used to slow it to landing speed. How can energy be conserved for a falling object? By removing air resistance. For example, on a planetary body that has little or no atmosphere, like the Moon, there is no significant air resistance, and total mechanical energy is conserved during a fall. 10.3 Friction. Other frictional forces also change mechanical energy to thermal energy. For example, if you lightly push a wooden block across a table, it will probably stop before reaching the edge. Its kinetic energy changes to thermal energy. The temperatures of the block and the table rise slightly. The increase in temperature because of friction is especially evident in vehicle brakes. Brakes use friction to stop a vehicle's wheels from spinning. After a car comes to a stop, its brakes are often hot. Overheated brakes can be a problem in loaded trucks or in any vehicle making a long descent down a mountain. Friction can also change mechanical energy into sound, i.e., acoustic energy. Some of the kinetic energy of a spinning wheel becomes the sound of squealing brakes. A creaking door results when friction at the door's hinges converts kinetic friction, often stops the squeaking. Not all frictional forces are obvious. A spring, for instance, has internal frictional forces that convert the spring's mechanical energy to thermal energy, or sound. The internal forces of friction in the spring eventually stop its oscillations, even if no external force acts on it. Most spring problems referred to in this textbook involve springs that have insignificant internal friction, another characteristic of an ideal spring. Ideal springs also have no mass, and they obey Hooke's law, F equals negative K delta X, perfectly. Ideal springs, like ideal strings, only approximate reality. When total mechanical energy is conserved. 10.4 Conservative forces. We have discussed frictional forces that do not conserve total mechanical energy. What about conservative forces? Forces that do conserve total mechanical energy. A conservative force between two bodies always pushes or pulls along the line, joining the centers of the bodies. You remember from Chapter 7 that this kind of force is called a central force. All conservative forces are central forces. One force of this kind is the force of gravity. Consider a satellite orbiting the Earth in a perfectly circular orbit. How much work does the Earth do on the satellite? Figure 10-5 shows that the satellite moves in a direction perpendicular to the force of gravity. Therefore, the component of the gravitational force in the direction of the satellite's motion is 0. The Earth does no work on the satellite as long as the satellite continues in a circular orbit. 10.5 Path independence of conservative forces. What if the satellite moves from its orbit? Suppose it gains altitude from point A to point B. How much work must be done on the satellite against gravity? Consider the path followed by the satellite in Figure 10-6a. Assume that the satellite moves from A to C to B. To move it radially, without acceleration, from A to C, delta H, opposite the direction of the force of gravity, will require a force with the same magnitude as the force of gravity, but in the opposite direction, Fg. The work done on the satellite is WAC equals Fg delta H. To move the satellite from C to B, no gravitational work occurs since the satellite moves along a constant radius circular orbit. The total work in moving from A to C to B is WAB equals WAC equals Fg delta H. What if the satellite instead moves from A to D to E to FTOB, as Figure 10-6b shows? The satellite moves from A to D and from E to F in circular arcs, so no gravitational work is done on the satellite. To move the satellite from D to E along a radial line, a force of negative Fg is needed for distance of delta/2. The work done against gravity is WDE equals Fg delta H divided by 2 equals 1/2 Fg delta H. A force of negative Fg is again needed to move the satellite from F to B, a distance of delta H/2. WFB Hersh Fg delta H/2 equals 1/2 Fg delta H. The total work done in moving the satellite from A to D to E to F to B is WAB equals 1/2 Fg delta H plus 1/2 Fg delta H equals Fg delta H. This is the same as the work done to move the satellite from A to C to B. In fact, any path from A to B can be thought of as a series of moves in the direction of negative Fg and perpendicular to negative Fg. In each case, the work done against gravity is the same. This concept is called path independence. For any conservative force, the work done on an object against the force depends only on the beginning and ending positions of the object. The work done is the same for all paths connecting those points. Suppose the skier in Figure 10-7 continues down the hill and over the hump. What happens to his kinergy? As he skis to point C, his potential kinergy changes to additional kinetic energy. Then, at point C, he begins to go uphill. His kinetic energy decreases as his potential energy increases. At point D, his potential energy is mgih hd equals mgih hb. Since his total mechanical energy is conserved, his kinetic energy must be the same as it was at point B, and his speed is again vb. As the skier continues over the hump and down the hill, his potential energy once again changes to kinetic energy. At the bottom of the hill, point E, his potential energy is 0, having changed completely to kinetic energy. What is the effect of the hump on the skier's kinetic energy at E? Since his kinetic and potential energies are the same at D as at B, his speed, and thus his kinetic energy at E, is the same as it would be if there were no hump, and he skied directly from A to B to E. This shows again that an object S energy change between 2 points is not affected by the path taken between those points. 10.6 Escape speed. When total mechanical energy is conserved, potential energy can be changed to kinetic energy, and kinetic energy can be changed to potential energy. As an object falls from a shelf, its potential energy changes to kinetic energy. If it is tossed from the floor to the shelf, its kinetic energy changes to potential energy. Similarly, when a meteoroid is pulled from far away in space and impacts the Earth's surface, its potential energy changes to kinetic energy. And when a spacecraft at the Earth's surface is launched away from the Earth, the kinetic energy delivered by its engines changes to potential energy. The escape speed is the minimum speed that an object of mass m requires to leave a larger object of mass m, so that mass m cannot return due to gravitational attraction alone. The zero-height reference point for the launch is the center of the Earth. Assume that total mechanical energy does not change. Delta E, delta K plus delta UG for OJ. Delta K equals negative delta UG. Substitute the kinetic and gravitational potential energy formulas for both sides of the equation. Then solve for the escape speed, which is the theoretical initial velocity at the radius of the Earth. VR 1/2 meter V infinite square, 1/2 meter VR square, equals negative GME over R. 1/2 V infinite square, VR square, equals negative GM over R. V infinite square, VR square, equals negative 2. GM per R, VR square equals negative 2. GM per R, V infinite square. VR square equals 2 GM per R plus V infinite square. VR equals score, root, 2 GM per R plus V infinite square. In this case, M is the mass of the Earth, M is the mass of the rocket, and R is the Earth's radius. The minimum escape speed can be calculated when the speed of the spacecraft at an extreme distance is 0. VR has square root 2 GM per R, 10.1. Notice that the rocket's mass did not affect the calculation. The escape speed depends only upon the gravitational force of the planet and its radius. It is the same for all objects within that planet's gravitational field.